In this screencast, I'm going to derive the geometric distribution, and I'm going to show an example of its use. It's a pretty simple distribution, and it's rather straightforward derivation. This is one of the more simple of the distribution functions for discrete variables. The geometric distribution is used to describe or predict the probability that you will have a number of successful trials before having a failure, or having failures before having a success. Let's do the latter, where we're going to carry out trials until we have a success. We might get lucky, and the first trial might be a success. So then we would have a success on the first trial. Okay, we might have situations where the first trial is a failure, denoted by an F, and then we have a success. We might have 2 failures before we have a success. We might have to go 3 failures before a success, so a success on the 4th trial, and so on. Here we're going to denote X is going to be the number of trial, and generally we are using the geometric distribution when we are asked what is the probability that the first success is on the Xth trial. Now if you had it reversed, where you want to determine what's the probability that you have the first failure on the Xth trial, then you could adapt this, but you just have to change around what you're using in these equations. So in general, we're going to have trials, and we're going to say we have failures, success. So these dots are all failures. So ultimately we're going to have a success, and once we have the success, then we're done. What is the probability that the first success is on the Xth trial? So this would be X, the number of trials. This then, omitting the final success at the end, would be X minus 1. To calculate the probability of having X minus 1 failures, that's just 1 minus P, where P is the probability of success, raised to the X minus 1. And if you watched my screencast on the binomial distribution, you noted that we had, in the binomial distribution, we have like an n choose x, because each of the different independent combinations contribute to the overall probability. We don't have that, because how many ways are there to have x minus 1 failures into x minus 1 spots? There's only one way to put these failures in there. So we don't need to have anything out front here. And then what's the probability of having success at the end? That's just P. This will give us the probability that the first success is in the Xth trial. I have an example here. You work for a pharmaceutical company that makes a product called Curazole. What is the probability that the first failure occurs on the 12th batch? And long-term production has indicated that the probability of a batch being successful is about 94.7%. So to solve this, we can use the geometric distribution. Now, you notice that up here in the geometric distribution, P is the probability of a success, but we're going to call a success, in this case, a failure. So really, we have to change our P to be the probability of a failure, which in our terms is a success, because the success in the geometric series is what occurs last. So we're going to go success, 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 failure. The probability of that happening is just 11 successes. The probability of a success is 1 minus 0.053, or 0.947. So we're going to have 11 successes, and then we're going to have a failure. So when we do the math, plug this in to our calculator, this ends up being about 3%. What that means, in conclusion, there's a 3% chance that the first failure occurs on the 12th batch.